All right, can you hear me? I think it's time to start. Okay, a couple of things before we start. This is our fourth week, and I'm receiving your response to the assessment. So I have to tell you that there are limited capabilities on Canvas. So for those of you, even it's an anonymous. So of course I cannot go, I can see your total grade, but I cannot go and see what you have said. What is happening now with grades is every answer you give is appropriate, obviously, all right? But I cannot find a way to give you full points for any of the answers. Whatever I do is that either it's gonna give, if I make all of the answers to be appropriate, correct, then it's gonna give every answer the same point, and then it's going to multiply. I mean, if there is something, so if I put 4, we'll divide 4 if I have 5 answers by 5, all right? If I put 28, then it's gonna, if I make 420 and it's giving you 4, then the total is going to be so much bigger. So your percentages, but I mean, I don't want to go into details. The bottom line is that after you respond, I will go to your total grades on the grade sheet, and then I will change them. I know how to multiply them by 5, for example, all right? Now, so don't worry about what you see until I find how to do what I want, and I need to call somebody to talk to someone. We're going to do it this way, specifically for the assessments. The quizzes are not a problem, all right, obviously. Now, the other thing in the assessment, it says, do you have a suggestion? Even if you don't have a suggestion, say no or none to be able to get the point. Because if you skip it, you miss the point that there is on this box. And many of you have made that. So just put none if you don't have a suggestion. Just don't skip, all right, that particular answer. None is a response, even if I'm looking for specific responses. So far, we have we have almost 50% of the class that has responded. And from that 50%, there is a large number of students who say that they have a problem with transmission lines or the material we have covered so far. They understand the lectures, but they have a problem with the homework. So I understand that. Usually the homework is supposed to be there to stretch to force you to work your mind. That's one thing, but if you are clueless about what the homework is asking you to do, that is a problem. All right. I mean, the homeworks are supposed to be not identical to what we do in class, just a little bit to stretch it above that to see who has been. I mean, I want to see differentiation. If you make everything simple, I don't know who has a problem and who can see things through. However, if you are totally unaware of what the homework is asking you to do, that is an issue. Why am I saying that? Because I will wait, of course, to see the rest of the class, and then I will present you what I found, hopefully this week, because we have an additional issue with homework. Due to some departmental issues, the TA for this week has not been assigned until Friday. So I'm correcting the homework, which is fine, but I have limited time in doing everything else. So I will try to finish homework 1 this week, and the TA will try from Friday until Sunday to finish homework 2. So I may be able to tell you about the first assessment by next Tuesday. If not, I mean, I may give it to you into different things. First of all, to look at the survey, and then to look at the grades, whatever I have by then. All right, so I need to know if you have difficulty as we move forward, because we cannot stop with transmission lines, as you can imagine, all right? This class is supposed to help you design a receiver. And transmission line is the ingredient. It's like you cook bread, and you have to understand that you need flour. And you tell me, I don't understand what that is. And I say, how am I gonna go beyond that if you have a problem with the fundamentals? Now, I did 4 so far problem-solving sessions. I cannot say that there was a whole group of people who came. There was one problem-solving session with one person, and there was another one with 6 out of a class of 78. Now I understand that you may have other classes and all of this, but Saturday is another day, all right? I mean, Saturday, you don't have classes. I know that for sure. Maybe you have other commitments. But what I wanted to say is that I'm running out of options on how to help you. And I cannot tell you that we can go through this class without understanding transmission lines. I just don't know how to make this work. And I don't want to fail a big number of this class, because that means that if I have indications that a big number is struggling and then I keep going, then something has to give. And so I want you to tell me how to help you for those who have a problem. Other than the problem solving session, I don't know what else to do. What else should I do? Think about it. If there is anything particular that I can give you and you can use it, let me know. So that's why your feedback is very important. Otherwise, as you will see, we are gonna move. I'm not gonna teach transmission lines in this class when we are supposed to bring receivers. Or I'm not gonna spend half a time transmission lines and then the rest, networks. And then don't even do a low noise amplifier. Don't do a mixer, for example. Then a receiver is not just transmission lines, all right? Now I understand why some of you have problems with that, but I cannot help you if you don't help me help you, all right? So that's what I wanna say. Okay, more on Thursday. But on the basis of what I covered so far, do you have any comments? I'm open for comments, this is an effort, this is a class to learn. It's not a class to judge you. I'm not judging you. I mean, grades, as I said, as a second step in my role to help you learn something. It's not I'm not gonna judge anybody. I mean, I'm not doing that. This is not my style, and I have already, as an adult, decided very early, mine is not something that I want people to do to me, and I'm not doing to them, all right? I don't like to be judged either. I like to receive suggestions, and I like to give suggestions, but beyond that, that's where, that's who I am. In any case, so I want you, don't be afraid to tell me, I think we need to do X in this. Why would you feel afraid to tell me that if you have an idea? Because if you don't give me ideas, I don't know what else to do. I'll do something, but may not help you. I mean, I may do, who knows, extra time, well, I don't know what. I mean, at this point, okay? So anyway, think about it. And yes, please. Of course.
So I want to take like the lack of attendance for the help sessions to like be an indication. So I haven't been able to make them. So
yes.
I can't make the week one because of class on
yes.
Saturdays. It's just so I'm not really there. At least for me, I'd be more able to take something during the evening throughout the week that I would be.
Okay. If you want me to move office hours to evenings, I'm not, I don't care, I'm an evening person, as a matter of fact. It may be like a little later because until I cannot do it here very late in the evening because I have to drive home. I'm commuting from the Woodlands. So I'm going to do it from home. I'm not a very early morning person, even if I can wake up very early, but I can work late. Now, if that is something, so give me that in your survey. This is what the survey is supposed to do, all right? If you think that by moving it to the evening, we are going to increase the numbers, I'm more than willing to do that. And you know why it is important to be there? And of course, you can see what I'm doing, but if you're not there, I don't know which part you don't know. I may pick a problem that, and you wish that I had picked a different one. Or the other thing is to send me suggestions for problems you want me to solve if you cannot make it. All right, I'm not going to make the change from where I have it right now to later if I don't feel that we are going to increase the volume. I mean, the crowd, rather. Because it's going to be for me a late thing. I'm willing though to do it. Like Saturday, do you want me to move Saturday? Because I have more flexibility on Saturdays. I can have one on Friday. I have more flexibility on Friday. So think about, yes. Okay. Friday evening. Okay. Okay, so Friday is better. Friday, what time? Like later? Friday evening? Not Friday evening. Okay. Like 2:30 to 4? Okay, well, all right. Now, listen, because of that, send me, that's why I'm doing the assessments, because I want to see the majority. They give me the statistics and then I can see statistically. Let me go there first. Yes. Okay, I can do that. Okay. I can send this other survey today, all right, that's a good idea. I will add all of the days of the week, with the exception of Sunday evening, because I'll tell you why. Because everybody goes there. And last year, the deadline was 6 p.m. Like 5:55, I have students on the Zoom who were trying to solve the problem. And that gets me, seriously, I'm not, teasing you right now. I have this issue about going too close to any deadline. Maybe out of all of these years of this work that I'm doing, that I have to meet deadlines as a faculty member, it gets me seriously stressed out and I cannot sleep at that night. That's why I want to protect myself a little bit. So Sunday, is the morning is good, or early afternoon, but not at 6 p.m. Done. And dead. There is no channel for communication with me after 6 p.m. All right, so I'm just telling you. So you have to manage it a little, but I'll send it. I'll send something. So, all right, I need to help you. We need to move forward, because you will see what we are gonna do next from today rather. Because if I don't do that, you're gonna go to the lab, which in fact I have good news for you in the lab, because we found a way to do the experiments from home. Yes. So you can put the loads, whatever you have to do. You're going to see a little bit, like a very brief visual of how the instructor makes the connections, but you can select from home. You can do it from the computer. We found the software to do that. So, we're trying very hard to accommodate all of you in this class, but you're not going to be able to, if now it seems like this, and something that is like that, and then really becomes like this, you're gonna fall off, right? Okay. Yes. And my mistake. I have to go fix it, but I will never ever give you homework for the same day. I mean, that doesn't happen, right? So obviously consider that to be, and I will fix it. Thank you for reminding me. Somebody else also told me, but forgot. Yes.
We had like last time you talked about, as far as like giving extensions, you had to put the homework solutions out by like the beginning of the week.
Yes.
So
today there were people who were, so up until last night I will put the solutions today. Okay. All right, so the solutions on Tuesday, because there are always people for one or another reason, and I don't want to have all of these people miss the homework for one day. All right, so as soon as I go back and after the observe, so that's what I'm going to do next, to put up the solutions. Okay. However, I have to say in the first homework so far that I have looked at whatever I have looked so far, I'm not disappointed. There are people who do things well, but we are a big class, all right? So wait until I see everything. Okay. Now, week 4, we are gonna always review transmission lines. So at least what I will always do as we move forward is to always talk about transmission lines and remind you of what we've seen. And that's how this class is. Transmission lines is the fundamental ingredient, all right? So it's not like that we're gonna leave it behind and then we're gonna see something totally different. You're gonna see that over and over and over again. So eventually you're gonna catch up. However, you don't wanna miss your grades, on your grades. All right, so today, what we are going to do is to start, and in fact, I'll go right here because it's easier for me. Week 4, network theory. And I have also included among your material also what is called, let me, in fact, for a second before I go there, let me go back and see. Okay, here. You see network theory. This one, it's from the books, from the chapters that I told you can have. All right, from the, well, from the chapters that I told you that you will have available. And I have reduced the size. All right, so it's very concise in what you're gonna read. And maybe I can do it from here for a second to show you what you will have to read this week. So introduction to, it's much easier if I don't have to go through Canvas. Okay, this is what I'm gonna do. This is what I've done. I took this section and I have reduced everything to only the material that you're gonna see. All right, so this is more like in boxes. You will see a little bit of that. There is gonna be transmission lines in some of the examples, but this is reduced substantially, and this is what you're gonna have as your guide, all right? I'm not gonna go over this from today in my lecture, but I'm gonna do more of a concise summary of what you're gonna see, and then we'll also get into details. Today in the lecture, we are gonna just introduce network theory. On Thursday, we are gonna do a few more things, and as we move forward, we'll use it. That's why we are introducing it. It's like think that now we covered, like you have a toolbox, and I'm teaching you about the tools that you will have to use. One tool set were transmission lines. The other tool set is network theory. And then from these two tool sets, we'll start thinking about filters, which is a component, all right? Then well, we talked about matching networks. We'll see them again in low noise amplifiers and so forth, and mixers and so forth. Okay, so today, I will start also, as I said, I will always remind you of the things that we have seen. Yes.
Turn on TV screens to show your
Okay, all displays. Table displays. Your device. Other. Okay, thank you. All right, so you need to remember, in this class, you will primarily use microstrip. All right, so however, there are two primary types of planar transmission lines that are used in industry. This is the microstrip, where the strip and the ground, two conductors, are separated by the dielectric substrate. And this is a W, all right? And here, what do you see that I have placed? I have placed an open-ended shunt stub. See that? This is a realization, a practical realization of this thing that we have seen. That's how it looks. In microstrip, you always prefer an open, unless the open, as you remember from the Smith chart, an open implies in impedance infinite, all right? In admittance, 0. Okay, remember those two things. A shunt configuration, however, makes us prefer what? Impedances or admittances? Admittances. A shunt configuration is parallel. And in parallel configurations, admittances add. All right? So if you have a shunt configuration like this, because you have the one conductor of the stub, which is this one, to be connected to the conductor, one conductor of the microstrip line, and the other conductor of the stub, they share the ground, obviously, which is here, is a common ground. So the grounds are connected, the tap conductors are connected, so it's a shunt configuration. In a shunt configuration, we prefer to work with admittances. And what is the load of an open-ended shunt stub in admittance form? What is the admittance at the end of an open-ended stub? 0. So when you are on the Smith chart, visualize the Smith chart. Can you visualize it? All right. Here, the Smith chart like that. On the left, what is the number we have? 0. On the right is infinite. When you're working with an admittance and you want to find the load of an open-end stub, where are you going to start? At the 0. And if you want to start at the 0 and you go this way because you want to find the input load, you are given the length, which way are you going to move? Clockwise. Remember, clockwise is always from the load to the source. The source is, to find the source, you have to move away from the load. Somewhere here. All right? So, in a given application, there are 2 possible terminations for a stub to get the same result in terms of whatever you need impedance, input impedance here. 2 possible terminations of the stub, different lengths will give you the same result. One is an open, the other is a short. One of the 2 terminations will be longer in length than the other. And if it's too long, you prefer the one which is shorter, unless the short is too short and you cannot make it, all right? Unless the short is 100 of a wavelength, so it's going to be like a tiny thing, you cannot make it, so you go to the next type. But if you have one which is over half a wavelength and the other which gives you a length shorter than half a wavelength, you always prefer the short. Why is that? Because if this is too long, it operates like an antenna. We're not gonna now do this in this class, but you need to remember that in realizations, also there are practical reasons for making a choice. All right, but we will learn more of this in any case. So this is like that. Now, why do we use this one? Why? You say, why am I not satisfied with this? There is a very important reason. So look at this. The substrate thickness here, if you are at low frequencies, we have substrates that tend to be in that wavelength. Lower frequencies, longer wavelength. Remember that, right? If you go to lower frequencies where you have longer wavelengths, a given substrate thickness can be practically very, very, very small compared to the wavelength. And you remember what I told you? I mean, I said 1,000 of the wavelength. It has to be definitely smaller than 100 of the wavelength to avoid high frequency effects. However, if I start moving my operating frequency to very high frequencies, it is possible that I violate that condition, that the thickness has to be less than 100 of the wavelength for all of these materials that I have available. And in that case, which happens with industry when you go to high frequency applications, all right, then people do not want to use that because no matter what you do, you're going to have high frequency effects. Parasitic effects means capacitances, inductances, everything that destroys your design, right? Unwanted things that you have not planned to include. They will be there and they will destroy your design. So instead of doing this, they thought, what can I do to bring my ground closer to my conductor? So what they did, they split the ground into two and they take it to the surface. All right. So a coplanar waveguide, let me start with this one here. You see what they've done? What we've done rather, because it was at the time when we were working on this. These are things that happened. This line, when I was an assistant professor, was doing, characterizing and developing all of these things that AADS has and HFSS and ANSYS or whatever. And there are things that we were doing research on in the 80s, all right? So why did we start working on these lines? Because then what did we do? We took the ground, say forget about this, we do it symmetric, cut it, and bring it on the surface. So half of the ground is here, the other half is here. So here, this line, I can bring the ground as close to this line as I want. Now, the difference with this line is now I have a symmetric structure. Instead of two conductors, I have three. But so what? You know, now I avoid all of these high frequency effects that I have to deal with. Which means that in a line like that, everything has to be symmetric, if I can. So instead of putting one open-end stub, in this one, I can do both open-end and I can do both short. This is open-end. In fact, what happens, excuse me, this is open-end, right? You see one ground here, the other ground there, they're not connected. The strip, which is the green, and the grounds are not connected, so that's an open circuit. The yellow here are the apertures. The problem is that I have to do it symmetric because asymmetries in this structure are not good. But I solved a number of problems, all right? And it's still the same problem, see? These two geometries are still giving me the same problem. It's just two different realizations. So for our class, we're going to use this because we're going to use low frequencies. And then you have here, why now I don't want to do this in microstrip, because I have to open a hole. I have to metallize the hole really well. And I have to make sure that the metal connects well with the ground. And the more holes I have to drill, or I have to make, the bigger the issues I have with my design. So if I want to do this, all right, and that's a serious, another. In fact, that's a serious one. Let's look at still the shunt. This is more complex. I will look at this. This is still shunt, but short. This is a short coplanar waveguide, much easier. I have no holes to do. All right, nothing to drill, no via holes as we call them, which in fact we don't drill them, we fabricate them. And it's a big deal. There was at the time when we started doing those via holes, they were a big deal in silicon because they have metallized them. They cannot be vertical and metallize them because all of the conducting molecules are coming like this from gold. You know, you shine them in a chamber that has low pressure, and then they have to see a surface to be able to go and stack. So the surfaces have to be like that. So it's not like a simple hole you drill. So all of these problems are gone with this one. And then people use it from that point on. And I will stop there. I will have this as just an example. The other example that you are going to see, but we're not going to get into this much issue, is I wanted to show you. You remember we showed that in one power amplifier, the circular wires, and then I asked you what those are, and you said they were inductors. This is an inductor. Now, do you see there is a small detail here which is extremely important? In this inductor, you have the coils, but the coils cannot cross. They cannot touch. They have to go like this, if you remember, right? Remember the inductors from a wire? The coils go around and around like this, but they don't cross each other. And then here, the way we make them is we do one layer on top, and then we go down through a via, and then to a lower level, and we do another round, and then another via to the lower level and do another round. So in silicon, in CMOS fabrication, this is how many metals you have. And then you use all of these metals. You remember I told you the top metal is thicker? This is for high frequency. So the higher you go, that's how you use your high frequency. You need thick metals. As you go lower, these metals are for digital. You don't need thick. All right. So just get it how, because we talk about things, you need to see how we are done them. We're doing them in reality. How do you design them? We're not going to do this here, but you want to see how people were doing it before we had ADS. Now you go to ADS and you can put your material properties and then all of this, and it's going to come out with a particular step. If you don't have that, then we work with equivalent circuits. Remember when I told you that if you find an RLC combination that has the same performance with a given component, we call this RLC combination an equivalent circuit. Remember we said that? We found one for a transmission line. We'll go back. This is another one. How people found it, let's put it aside, somebody found. They considered all of the effects they have. If you have conductors close to each other, you have capacitance. If you have lengths of conductors, you have inductances. If you have resistive conductors like full conductors, or not, or if you have conductors with finite conductivity, you have resistances. So everything that you see here, capacitor imply two metals close to each other. Inductors imply a length of metal, right? Resistors imply ohmic or dielectric loss. That's how people develop that. After you develop it and you know how this relates to the different geometries, that's how people will take these equivalent circuits and then design them, do different things. Not anymore, you will not have to do it, but just to get an idea of how we really analyze our circuits, all right? Okay, that is to put some things into perspective. Now, at this moment, we are gonna leave transmission lines for a second, and we are going to another tool from our toolbox. And this other tool is called network theory. Okay. So what we're gonna do today, I will introduce to you how new representations, yes. To do this again? Okay, I have two Zooms. Thank God, one was not, the other one is on. I think both of, am I not connected to Zoom?
In the bottom there, it says muted.
That's okay. Don't worry about that, as long as I have the recording. Unless it's on both of them, Zoom. I have unmuted here, but let me see what I have here. No. Here, okay, don't worry. In one of them, if I use both of them, I have feedback. You know about feedback. Voice goes to on, is amplified, goes back, and then you hear this thing. Okay, so we are trying to avoid feedback. You have to terminate. I mean, you have to mute one of them. Okay, so we're good. The only thing that if I'm totally out of Zoom, then it's a problem. All right, so now we are gonna introduce matrices. We call the matrices network parameters. Okay, to see the value of these, we take something that you have already designed, something like that you have already seen, okay? It's very generic. So you have a section of a transmission line, D1 is 01. Another section of the transmission line, D2 is 02. A third section of the transmission line, D3 Z03. Okay, so now we have this circuit. And let's assume that all of these are defined, right? Whether all of these parameters are known in this particular system. So then, do you remember I told you the input is called port 1 and the output is called port 2? We call them ports, either A prime or B prime, but they are ports. Input port, output port. Right? Now, first of all, at every port here, we don't have a source anywhere yet. But assuming that I had a source somewhere, either on this side or on this side, I would have a total voltage here and a total current across there. All right, and I have used this, where is the positive? The current flows out of positive. This is the standard that we are using, all right, to represent that. Even if we know that this is changing in terms of time, but every time you have a plus here, the current is going to flow in. Every time that flips, the current flows out, all right? So the two go together. Okay, so now that's how we represent it. P1 here, I1 that flows in. For symmetry, I2 here in the representation. Symmetry in the representation, I2 here, and this V2 goes out. So practically, this we have put all of these things in a box, and we could call that the two-port matching network, because at some point we designed it to match a load to a source. So after you did the design, you put it in a box and you say, well, this is a two-port matching network. Now, in design of complex circuits, as you know from digital designs, when you want to develop a microprocessor, you don't have 1 million transistors explicitly sold in 1 million locations, and then 10 million lines, conducting lines that connect them. Nobody does this kind of simulation. We don't have even an HPC. I mean, do you know how many transistors we have in the iPhone? How many? A billion, not millions, 1,000 times that. That's how it goes. Now, people who put this together, they don't analyze 1 billion transistors and 10 billion lines. There is no HPC on this world that can do that in any decent time. What do? They go down to building blocks that eventually repeat, because in any design you will see there will be building blocks that repeat. Like a receiver, if you have 10 receivers on your EM sensor, each receiver will have more or less the same kind of design. All right, so you're not going to sit down and put all of these 10 receivers and then try to analyze this thing that you're not going to be able to do. You're going to put fundamental units in boxes. You will call them basic units, and then you will represent those with matrices. So then, instead of having this unit here, it's very simple here, but I could have multiple lines, multiple stubs, I could have multiple other things in there. And then it would still be a two-port matching network. And therefore, I reduce this complexity by going down to something like that. Now, when is this representation valid for me? If this matrix can be defined out of the fundamental components of the unit that I put in the box. So the moment I can find the elements of this matrix as a function of frequency, I have a full representation of these facts without even knowing what is in there. Practically, I don't need to know. So if you were a designer and I am a master student or an undergraduate student who works in the lab and I'm trying to help you, you're not going to tell me to put down all of this. You're going to give me this matrix, and then you will tell me, go and put many of those together. And you will see how you do that, all right? So you start reducing complexity as you increase complexity. See what I'm saying? There is, to go to a higher level of complexity in the circuit, you reduce your representations. So you go down to this. This matrix is called the impedance matrix. And we use these elements. Now, why am I doing this? Because these are definitions that people, when I tell you, give me the impedance matrix of this, you have to know what I'm talking about. And the impedance matrix is usually a matrix that connects the voltage and the voltages of the two ports to the currents of the two ports. And the elements of the Z matrix, we call it impedance because they have units of ohms. Okay. As we have introduced the impedance matrix, of course, there is an admittance matrix. And how do we define it? Now we relate the vector of the currents to the vector of the voltages. And this is an admittance matrix we will show like this. And don't tell me when we do that this is the inverse of that and this is the inverse of this. Okay? The matrix as a matrix is the inverse of this as a matrix. But the inverse of a matrix is not like a matrix that has elements, the inverse of all of the elements. All right, be careful about that. Okay, so we are going to see this more detail later. Transfer matrix, of course. Now we play with how we place B's and I's. And the transfer matrix is where now I isolate port 1, P1, I1, from port 2, P2, I2, and I call that the transfer matrix because it really transfers to me, for example, V1, I can find V1 in terms of V2 and I2. I can find, if you give me this matrix, or you give me these two, I can find these two, all right? Or if you give me these two, I can find these two. Transfer matrix. Now, these are these three matrices that they look at the total voltages and the total currents. Make sure the time. Okay. We are going to use another matrix more than these ones. And I will tell you in a second why. Those total voltages and currents, all right? Before this, before we go to below. Do you remember in the previous one where what I used as convention for Z matrix, Y matrix, and T matrix? The convention is all of the currents flow into the network, and these voltages are like that. All right. Now, if I want to connect two of these networks, all right, let me just do something here. We'll see it also later. But let's assume that I want to connect two of these networks. You will find out that the matrix that I have just introduced, the transfer matrix, is not very useful. Why is that? Because if I say I want it here, let me increase that. I wanted to put this one here. Next to this one here. All right, the currents, this current will flow here and here. But these currents for the other one will flow here and here. And therefore, I have to change the signs, and that makes it complex. So people find that the transfer matrix makes sense when you look at one single network, but if you try to cascade networks, the transfer matrix is not very useful. So because of that, we introduce another matrix. And what we did in this other matrix is we just change in the definition the direction of this current only. So that flows into the network. This is plus and minus, but that flows out of the network. This is plus and minus. Why is this important? Because now, if I put two of these cascaded, and my currents go like this, then I can cascade the new matrices that I define. I can multiply them without necessarily having to change anything. All right, so now I'm introducing, we will see that later. So I'm not gonna go into details with each one, with any one of them, until you see the whole picture. And that is what I'm presenting to you right now. So we just make a small change in the direction of the current. We introduce a new matrix, which is extremely useful, very useful. And that is the ABCD matrix. And what does this do for this new P2 and I2? So the output now, also we change the direction, the vectors, right? We put the output vector first, the input vector separate. And this is the matrix that gives the output vector from the input vector. All right. And this is called the ABCD matrix. So A is the first element, B, C, and D. This matrix is extremely important. We are going to use it multiple times. But before we go and talk about that, now let's look at the other representation. Also, an important one. The two last matrices are the most important that we have seen compared to the first three that we've seen. All right. This one, it does something different. We say, okay, instead of no, that is a problem here. Let me just do something. I was working last moment to do this. So this should be all right. What this one does is something interesting. We define the input voltage, the incident, and the reflected, because we know, we've seen in transmission lines, have we not? We have seen in a transmission line like that if you put a source here, your total voltage will be on this transmission line will be the sum of the incident and the reflected. Okay, and then of course at the load, you're gonna have also a total voltage, and that is gonna be the sum of also an incident and a reflected. Incidents are those that go into the network. Reflected are those that come out. Now, the matrix that connects the reflected voltages from the incident voltages is called the scattering matrix. And this matrix is extremely important. Why? Because in industry, all of the devices that we are purchasing, including transistors, all right, active device, not only passive, if they're going to give you any matrix, it's going to be this one. So for example, you will see when we do low noise amplifiers, when they tell you that what is a low noise amplifier, it's nothing else but a transistor with an input matching port and an output matching port. All of the transistors, one transistor can be a low noise amplifier if you match it in a particular way, or it can be a different type, even not a very good one, but a power amplifier if you match it differently. Or it can be an oscillator if you match it differently. A transistor. All right, so matching, of course, is extremely important because it changes the performance of a particular device. Okay, when then you go to select your transistor, I'm giving you a transistor, say go and use this transistor to develop a low-noise amplifier. The transistor is gonna have this, you will go to industry, go to HP, and you look at every transistor you wanna see, say that operates at 3 gigahertz, is gonna come with many tables that will show you around below that frequency range, which is the design, and above it, the values of all of these 4 parameters as a function of frequency. That's how you're going to get it. This is how it's measured. All right? Nothing else. So that's what they're going to give you. So from there, you have to take this and try to match it. So we need to know how to use this and what it takes. Okay? So let me give you now some examples of how to do that. We'll start with a very simple example, and then we'll go to something more complex eventually, not today if we don't have enough time. Any questions so far? Yes.
So are these the values that B and A?
Yes. It's very interesting. I'm going to come into this, all right? So the ratio of these two is the reflection coefficient at the front, all right? The ratio of these to that is called the transmission coefficient, how much it goes through, all right? And the reverse when my source is on this side. V2 minus over V2 plus is my reflection at this port when I am looking it from this way, when my source is here. That's it. This is exactly what it is. And that's why it is important, all right? Because you want to know how much reflection I'm going to get from a device if I connect it to my network. And every time you try to create a matching circuit to this, it means matching. What does it mean here? But if I design it, let me in fact do this as an example, all right? So I have a table here that is in the book. I just want to remind you as a parenthesis. If somebody gives you A, B, C, and D, I mean, here you can find this. We'll have some examples how to do that on Thursday. If I give you one impedance, you can find A, B, C, and D. And from A, B, C, and D, you can find all of the scattering parameters. That's another table in your notes, which I do not have time to attach. We'll see it on Thursday, all right? So for very fundamental circuits, these are 3 admittances, 3 impedances. This is a pi combination, this is a T combination, this is a transformer, this is an open stub in series, this is an open stub in shunt, like I did. So here, for that, you have it, if you don't have transmission lines connected. So we will use one of these. We are going to use as an example. I will ask you to find for it or in one of the homeworks, but I'll do an example first on Thursday. Okay, so now let me do an example for in relation to scattering parameters. Okay, so calculate the example, the question, the problem can say, calculate, say scattering parameters of a section of a line, just simple like that, section of a transmission line. Okay, so what I do have here is this, I'm designing a section of a line. There. Then I take this here. And let's assume that this is a Z0. All right, and this is what? A quarter of a wavelength. No, in fact, yeah, lambda over 4. Then we in fact call it Z01. And then I'm gonna find the scattering matrix for this section of the line. Now, I'm operating at one particular, I'm designing at one particular wavelength. And as you will see, this design wavelength is the one where this distance d of the line is lambda over 4. So at the design wavelength, lambda naught, let me write it better, lambda naught, I have a section of line which is a quarter of a wavelength. And now I want to find practically let me, in fact, do I want to consider different characteristic impedance? Yeah, I will assume that at this point, this is connected to a line that has a characteristic impedance of, okay, well, 1 second, let me do this. All right, let's assume that this line is 50 ohms. 50 ohms. All right, so Z naught, 50. This one also is another transmission line with input and output characteristic impedance is 50 ohms. Also Z naught is 50 ohms. And this section of the line has Z01 to be, say, 70 ohms and is a quarter of a wavelength. All right. If now how do I find the scattering parameters of, in fact, I will move my reference plane to, you know, how I'm gonna do it as the following. If it's 70 ohms, I'll show you how I'm gonna draw this myself. If it's 70 ohms, okay, this one, visually, I will make it like that. And this one, visually, like this, to show that they are smaller. That's how I'm doing it, to visually connect this, to show that this is a lower impedance. All right, so Z naught, 50. And then also, this one is lower, and this one here lower. All right, and this is 50, and then here it's 70. I want to find, therefore, these are my input and output ports. I want to find the scattering parameters at this reference plane. And let's assume that the reference planes are just next to the transition from the 50 ohm to the 70 ohms. We are going to continue that next time because I don't think, well, we may be able to finish it because it's a simple one. All right, now, let's think what happens in this line. When assume that I excite it from this side and then it's matched here, all right? So I will assume in this one that we, let me, okay, I'll eliminate some lines so it becomes easier. And then 50 ohms here, you remember that? Or I'll put it underneath it. So we need to get rid of some of these things. And then you remember this. all right, because I'm gonna write there. And then we know, therefore, if this is Z naught here, let me put it Z naught here, Z naught is 50. All right, let's assume that I have now, I excite that line, which is my port, with a 50 ohm source. I'm gonna redraw it and do better before I upload it. And then let's assume here that I have matched this section of the line with a 50 ohm load. 50 ohms. All right, so practically in this case, I have matched input line. And if you exclude this, I have a 50 ohm. I'm matching at this point here between my source and this line, even if I have something else behind it. But my output line is matched and my input line is matched to my source. And now I want to find the following. I want to find that if my input voltage is B1 plus, then I know because of this structure, I'm going to have a reflection. So practically, I'm going to have a reflected voltage here, which is V1 minus. And in here, since this is matched, I'm going to only have a V2 minus. All right? Whatever goes from here, from this 50 ohm line, here is going to be matched. I'm not going to have another reflection from here. The only reflections I have are created by this structure. Right? It's a structure connected to two 50 ohm lines. So I can solve this problem. How would I solve this problem? Let's see. How much is V1, first of all? To find V1 is what the source exerts on this line. If this line were to be infinite long, an infinite long 50 ohm line, if this V was 1 volt, how much? Okay, so if we had this one, let me just do it for you here separately. 50 ohms here, 1 volt here. And then connect it to a 50 ohm infinite long line. How much will be my incident voltage? Let's think a little bit about that. An infinite long 50 ohm line, what kind of input impedance does it bring here? How much is the input impedance of a 50 ohm infinite long line? 50 ohms. All right. So if this line if none of these were to be here, so I had only this, but infinite long, what that would be will be half of this voltage. All right. So will be half a volt. So I know from here, so this is observation number 1, that my V1 plus is going to be half a volt. Okay. Now, if I had here a 50 ohm line connected to a 50 ohm load, how much will be the load here? How much is this therefore? Let me put this a little closer and then show you the following. I have a 50 ohm line which is of some length, 50 ohms, and I connect that to a 50 ohm load, 50 ohms. And let's assume that this length is D1. How much is the input impedance here? 50 ohms. These are fundamental things from previous class. All right, so these are the things you need to remember. An infinite line, a 50 ohm line, is going to show at any point an 50 ohm impedance. A 50 ohm line terminated in a 50 ohm impedance at any length is going to also show 50 ohm impedance. So this is 50 ohms. 50 ohms. So practically, what do I have here? Here I have a 50 ohm that load that terminates my 70 ohm line. So practically now I can remove the output port, all right, from here. Copy. I can put it here, paste. All right, I can now eliminate this. Do it a little thicker. All of these. And I can assume that here I have connected a 50 ohm load. 50 ohms. All right. Now, how much is the impedance at this point? At this point on the line, this is a quarter of a wavelength line. Let's call it, what do you want to call it? Say, call this one. How much is the input impedance that I see right there before I reach the transition? All right, I'm right here. Very close. This is my Z input at 1. How am I going to find this for a quarter wavelength line? What have we seen in the class? Yes.
So one over the it's a wavelength, so it's just.
Yes. So, but we have to put it carefully, all right? So we know that for a quarter of a wavelength, Z01 is the square root of the load, which is 50 ohms, times whatever impedance you see from the front, times Z in 1. That's the fundamental relationship of a quarter of wavelength line. So why is it that not the inverse of the impedance is true if your impedances are normalized to the same, all right, and then to Z01. So be careful when you say the inverse. It's true when you normalize everything to the same characteristic impedance, all right? But this one is the relationship. Remember this relationship, the Z01 square is the square root of these two, the load and the input impedance. So if I know the input impedance, how much it is, and how much my load, I find the characteristic impedance, which we did as an example. However, if I know Z01 and I know my load, then I need to find the input impedance as well. Yes. Excuse me, should be Z without the second. Thank you. Yes, this one, sorry. All right, it's a second part without the square. So this one. So therefore, it's going to be Z01 square equal, divided by 50, is going to be Z input at 1. And as a matter of fact, since Z01 is 70, it's going to be 70 times 70 divided by 50. How much is that? 490 divided by 5. Is 994. Is 94? 98, sorry. Yeah. All right, so that is 98 ohms. So now I found from here, but I use this. Well, no, this is okay. So this is true when it's a quarter of a wavelength. All right. So then, anyways, let me use that 98 ohms, and then what do I have here? Between the first combination, I mean, in fact, what do I have right here? What I will have there is the following: a 50 ohm line, all right, which is excited by a 50 ohm source, but very close to the line. Remember where we said that? So that distance of the line is very small. And here is connected to an impedance of 98 ohms. So if this dimension is very short, practically, and it's 50 ohms is matched to that. So here, the length of the line by itself is not going to have any impact, all right? The impact is going to be the mismatch between 50 ohms and 98 ohms, because this is like almost this abex, if you think. So now, how much, if the incident here, V1 plus, is half a volt, how much is my reflection coefficient here? My reflection coefficient there, which is V1 minus over V1 plus, is going to be 98 minus 50 over 98 plus 50. And then from there, I have 48 divided by 148. Am I right? Kind of. And that is going to be V1 minus times 0.5 volts minus. And from here I have that V1 minus is going to be 0.548 divided by 148. How much is that? It's about almost 1/3. All right. 0.5 divided by 3, 0.115 something. This is how I'm doing calculations, 0.166. All right, almost of a volt. So now, when I did this problem, I found for a given V1 plus, I found the V1 minus. Since the problem is symmetric, if I reverse it, it's going to give me the same thing. All right, so for a V2 plus, I find V2 minus. If this is 0.5, then this is going to be 0.16. If this is 0.5, then this is going to be 0.16. All right, because it's a symmetric structure. It does not matter from which side I see the same thing. All right, what is it that I have not found yet, which we are going to do next time, and I will rewrite that to see. And we are going to review it. What have we not found yet? What we have not found yet is V2 minus. We have not found yet how much voltage applies to the 50 ohm line here when this is connected to a quarter of a wavelength and when it is excited by half a volt. If we find that voltage, which we're going to continue next time, I will review the problem and continue next time, because it's also, you remember transmission lines, all right, by doing that. Then practically, I will have for a given V1 plus, V1 minus, and V2 minus. So I will have S11, S12, and then because it's symmetric, I'm going to have S21 and S22. So you will see that, all right? So out of solving this problem, we find the scattering matrix. So the scattering matrix is nothing else but a reflection coefficient at the front and a transmission coefficient through your network, all right? S11 always reflection coefficient, S12 or S21 transmission coefficients. And for passive networks, the transmission matrix is symmetric. So you know that. For linear and path, obviously. All right. We'll continue next time on Tuesday.
I have some questions about the quiz.
Yes. Yes.
So, number one, so for TM transmission line, it says, yeah, the field depends on direction propagation. I found out the ENH is defined by being normal to direction propagation.
So a transmission line TM when no electromagnetic components are along the direction of propagation.
I think that's what I put.
And what did you come out?
So I can zoom out so I can.
Okay, let me check.
Yeah.
So it might be, when did you get